This is quite an introduction. First, I would like to thank the SPA Executive Committee for the honor of selecting me to give this talk, being a Van Allen student for some 50 years ago. And of course, I want to thank my longtime friend and colleague, Len Fisk, who has, as we all know, been a distinguished leader in our field for the very generous introduction that you all heard, and it's a real honor. Of course, you all realize that in all of these cases, when it sounds like an individual effort, it's really not. It's all my colleagues and associates and students and that did a lot of the work that I'm given credit for. So I'm very grateful to them, and I dedicate the talk to them in this particular case and the honor. Let me, this talk, I selected the topic because I look at our community these days, and a lot of them probably don't know very much about how we all came to be in this business and the history of discovery. So it's more a history of discovery than about the detail of the science. And I drew a lot of material from the book Opening of Space Research, Dreams, Technology, and Scientific Discovery by George Ludwig, that was published by the AGU in 2011. And of course, my association with the University of Iowa from 61 to 68, and then the Applied Physics Laboratory at Johns Hopkins from 1968 to the present time. Explorer 1 was launched about a little over 3 months after Sputnik was launched, and Van Allen was the principal investigator for the instrument package. You see here his picture on the cover of Time magazine, and also down here at the bottom you see the iconic depiction of the Van Allen belts. There are the Ason belts that the press actually named Van Allen belts. He himself never called them that. But as soon as the discovery was announced on May 1, 1958, people began to associate the discovery with his name. And beyond that, you see the two Van Allen probes that many of you heard talks about in this particular meeting. And it's actually the first mission for NASA that was named after Van Allen, in honor of Van Allen, admittedly the person who one could say is the father of space science. So, his background, born in 1914 in Mount Pleasant, Iowa, was valedictorian at the Mount Pleasant High School in 31, Iowa Wesleyan College in Mount Pleasant, majored in physics and graduated summa cum laude in a class of 38 in June of 1935, and was mentored by Professor Thomas Poulter, a geophysicist who was a hands-on experimentalist, and Van Allen learned a lot as a student of Professor Poulter. He did his graduate work at the State University of Iowa, as you might expect, with getting his MS in 36, PhD in 39, both in physics. And he built the Cockcroft-Walton accelerator that measured nuclear cross-sections. That was the sort of the beginning of nuclear physics in the decade of the 30s, and he was doing a lot of work everybody was doing a lot of work in measuring nuclear cross-sections. And I actually remember seeing the Cockcroft-Walton when I got to Iowa City in the fall of 1961. These are some of the pictures of Van Allen. This is one of his in the, I think when he was about 40. The iconic image of the success of Explorer 1, where Bill Pickering and Vernon von Braun with Van Allen raised the backup of the payload. Van Allen's picture, of course, on the cover of Time. This is at the Air and Space Museum. This is in his office in the Building of Physics and Astronomy, and here is his office on the 7th floor of Van Allen Hall, which was a building named after him while he was still alive, of course, at the University of Iowa. And it was, just as you see, cluttered with books and papers everywhere, with, some of you might see this Frieden calculator down on the desk. I'm sure most people here don't know what I'm talking about when I say that. So he graduated, left Iowa City, went to Carnegie Institution, Department of Terrestrial Magnetism, to work with Merle Tuve as in his nuclear physics laboratory. And he met many of the luminaries of the day, Scott Forbos of the Forbos decrees that some of you know about, of course, Chapman and Bartels, the book of Chapman and Bartels, some of us grew up on as graduate students. In 1940, of course, we all know what happened with the war breaking over, and Tuve essentially converted much of the institution's effort to the development of proximity fuse to increase the effectiveness of naval anti-aircraft fire. And Van Allen joined the National Defense Council Office of Scientific Research and Development that was led by Vannevar Bush. In 1942, Johns Hopkins essentially decided to take on the development of the proximity fuse and establish the Applied Physics Laboratory, and Merle Tuve became its first director. So that's where APL came from. And Van Allen's principal focus in the proximity fuse work was to develop rugged miniaturized vacuum tubes. Remember vacuum tubes? Some of you probably heard of them. And they had a glass enclosure, and that vacuum tube had to withstand an acceleration of about 20,000 Gs. That may explain how Van Allen came to be a leader in instrumentation on satellite instrumentation and rocket instrumentation. He had that kind of an experience. In 1942, he was commissioned a Navy lieutenant and was dispatched to the Pacific to teach the Navy crews how to use the fuse. This is a picture of Van Allen at his APL desk with his uniform and also proximity fuse. And you can see it sitting on his desk, and you can get a sense of scale by the size of the book that is sitting next to. So that was it. And of course, we all know in history that the proximity fuse was a fairly important technology in the war, both in Europe and both in Pacific and in Europe. Okay, well, then the war ended. The years leading up to the IGY, 1958, he established the High Altitude Research Group at APL, which was the forerunner of today's space exploration department. He instrumented the V2 rockets that had been captured together with their German inventors and crew, and instrumented with cosmic ray detectors, UV spectrometers, magnetometers, ozone sensors, IR and visible cameras. Pretty good payload, you have to admit, by even by today's standards. Oversaw the development of the Aerobee high-altitude research rocket. He managed that, and many of them, over 1,000, were fired through 1985 when the program was discontinued. And then he was a participant and eventually led the what turned out to be various panels, national panels, the V2 upper atmosphere panel that became upper atmosphere rocket research panel and so on. And it culminated with a rocket and satellite research panel in April of '57 that essentially organized and ran U.S. effort in space until NASA was established in October of 1958. He moved to the University of Iowa, SUI, State University of Iowa, in '51, and established a very capable group to continue and advance high-altitude research. And they made a lot of important discoveries. I will just only say a couple of things, but these are some pictures of the group at APL with the a V2 nose cone, sorry. And here's Van Allen. This is the first high-altitude picture that obtained the curvature, that you could actually see the curvature of the Earth. And this is a V2 getting ready to be launched in White Sands in New Mexico. Van Allen had a lot of stories that he told some of his graduate students about those years. There's no time to talk about. Then, or could be talked about. In the process, they developed the so-called raccoon concept, where you took a balloon and hang a rocket under it to take it up to altitude and then actually fire the rocket and go to a lot higher altitude. And these are pictures from the cosmic ray survey on Navy ships that work north and south to get a latitude survey. These are the groups that were holding on to the rocket while the balloon was getting away from the ship. And in fact, at one time, they kind of lost the rocket and it started swinging over the ship and it almost hit the bridge, and everybody got terrified because that would have been not a good show. This one, I mean, this is up in the Arctic during one of these launches. Now, many of you might have heard the discovery of soft radiation, and this shows a typical count rate of a shielded Geiger counter and a thin window Geiger counter. You can see the rise of the balloon. Then at this point, the rocket fires. This is the altitude, by the way. And all of a sudden, they see this very large increase in soft radiation, as they called it, but not much of an increase in the shielded Geiger counter. And it's remarkable to read the papers. In 1957, Van Allen said, well, you know, these are probably not electrons, they're probably X-rays from precipitating 10 to 100 keV electrons. And he was dead on. I mean, that's what it was, not knowing much of anything else. And then they did a latitude survey, and lo and behold, you know, the maximum in soft radiation was mapping the auroral zone. Now we all think it's a duck soup these days, but at that time, they didn't know whether they were coming or going, as you will see from this particular plot, which is, don't know how well you can see it, it's a count rate versus time, and you see an increase in counts up to a given point, and then a decrease in counts. This is from Explorer 3, and Van Allen did this in a hotel room in Washington. You might say why that's significant. I'll get to that in a moment. But this was the count rate going up to a point, and then stopping to increase, and then it went down to on the other side. And this was 128 counts per second, which happens to be, you know, to the 7th counts. They were scaling the count rate, and they didn't think that they needed very many counts to map the auroral zone. Well, all of this became possible because George Ludwig, I'll say, you see his picture, had a digital recorder on Explorer 3, and for the first time they were able to essentially get a full pass. And when they did get the full pass down, what they saw was that the count rate went from this level up to 128 counts per second. Then it dropped to 0. Then it went up to 128 counts per second, came down again, and then it resumed its count rate due to cosmic rays. So there was a big question, what was this all about, and what we all do when we run into these kinds of problems in doing instruments. We actually calibrate the instrument. And they put the Geiger tube in an X-ray beam, and they had the right kind of scaling, and sure enough, it went up. Of course, topped out at 128 counts per second, and then it came down to 0 on the other side as the intensity was going higher and higher. And to understand this, this is what we were doing, the so-called R versus R curve, the apparent rate of a Geiger counter versus the true rate. And you see the Geiger tube behaves linearly up to about 1,000 counts per second. But then it begins to lose counts. And it hits about 3,000 or 4,000 counts per second. And then if you drive it to higher intensities, the pulses become so small that you can't trigger your threshold anymore. And eventually they become so tiny that it all goes to 0 through continuous discharge. So lo and behold, what happened when they were seeing this going down to 0 is because the intensity had gone so high that it just overdrove the Geiger tube and it was dead. And Van told me that after the Explorer 1, when they first saw the data, Bill Pickering from the Jet Propulsion Laboratory called him up and said, well, Professor Van Allen, I'm sorry, but your equipment ain't working. It's showing zeros. So it took a while to sort all of this out. And these are the people who actually figured it out. Carl McLuhan, Jim Van Allen, George Ludwig, and Ernie Ray. They have passed on. Carl is still with us. And these are the chart recordings that you could see, which are the way we got data those days. They got data. This is Van Allen's favorite figure in conceptualizing the particle trapping in a dipole field, and he went to Stormer's work back in 1907, and it showed how, once they understood that they had trap radiation, how a particle would mirror at the strong end of the magnetic field and then go back and oscillate back and forth. Nobody knew, of course, how it got there to begin with, but nevertheless, if it did, that's what it did. And the Van Allen et al. Initial sketch for the Earth's radiation belts. You can see the inner belt, the outer belt, the horns, as they call them. And this goes after the, I believe, Pioneer 1 or 3 went out and fell back into the Earth. That's what these two lines are for. And they finally figured out exactly what they were looking at. Now, being Greek, I had to insert this. I borrowed this slide from Yanis Daglis about Nicholas Christofilos, who was at Berkeley, Lawrence Livermore, I believe, and he proposed in 1957 in an unpublished memorandum that Van Allen had that charged particles could be trapped around Earth, and he proposed an artificial radiation belt due to beta decay could be created by exploding one or more fission bombs at high altitude. And that became the Argos project, and it actually was done. And you can find the paper in JGR in 1959 that demonstrated that you could actually do the trapping, and it was, in fact, so intense that it knocked off a couple of the early spacecraft, including one that APR had built. Anyway, now, I'm not going to get into any of the science, only to remind ourselves here that the Van Allen probes are making discoveries, and this is from a paper by Baker et al. In Science last year, where they noted the intermediate storage ring, as they called it, which had a 3-bell structure. And I'm mentioning this because I also use something else that's of interest later on. Anyway, these were the early days, and APL had invented the transit navigation satellite system. They wanted to find out about the space environment. They were too busy with the navigation aspects, so they called Van, and they said, hey, how about you of Iowa building a small satellite? And that's where Engine 1 came up, was initiated. It was the first university-built satellite. And you can see the stack here, and the bottom one is from NRL, is GREB-3. It was the first signals intelligence satellite. All of this is unclassified now. And it so happened that from the data from Engine 1, I did my master's thesis on solar protons over the Earth's polar caps. I got into the business of building instruments, and this is a picture from way back with Tom Armstrong and myself when we finished the instrument package for Explorer 33. It was called Anchor Deep in the Planetary Monitoring Platform in 1965. We never actually made it into orbit around the moon. We got into a looping orbit. But the next one, Explorer 35, actually did get into orbit around the moon. Anyway, the first mission to Mars came about, and it was launched on November 30, 1964. This was also my first instrument. Van Allen called me to his office about, as soon as I got my master's, about 16 months after getting to Iowa City, and says, how would you like to build a detector for the first mission to Mars? I said, geez, what do I have to do? He says, all you have to do is invent a detector that is only sensitive to protons and is not sensitive to electrons, so we could separate them out when we look at the radiation belts of Mars. And I said, geez, I'm not sure I know how to do that. And he said, he says, you learn. And sort of, that was his teaching method, throw you overboard and see whether you could swim. And I finally got it working about a month before launch. But that's where the discovery of solar electrons came from. We could tell the difference between electrons and protons. Anyway, this was the day of flyby on Encounter, 15 July 1965. This is Van Allen, and this is yours truly. And you see we are all looking at something. And that's a strip chart recorder watching data coming back from Mars at the, it's coming back at the speed of light, but the rate left a lot to be desired. It was 8 1/3 bits per second. Bits, not kilobits, bits per second. And our part of it for the trap radiation detector was, I think, about 1/4 of a bit per second. And you watch the recorder go click, 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 count. Anyway, so that's the technology of that day. I'm sure most of you don't believe this, but it's actually true. This is the Mars flyby data, and the principal thing to notice is that these are the 40 kilovolt electrons, the 150 kilovolt electrons from two directions. This is my solid state detector, and it actually showed an increase, but we interpreted it as being due to solar protons and had nothing to do with Mars. This was the point of closest approach, and at this point, and nothing happened. You know, everybody thought, hey, Mars got to have Van Allen belts, calling them that. So what did we do? And this should be a lesson to all of you youngsters in the audience on what you can do and how you can get some physics out of seeing nothing. Okay, so, well, we decided to do the scaling of equating the pressure of the solar wind with B squared over 8 pi. Everybody knew about that. It was proportional to the magnetic moment over R to the 6 squared. So you derive a scaling relationship between the radius of the magnetosphere of Mars to that of Earth, and this is the scaling relationship. And then we plotted the trajectory of Mariner 4 and various kinds of magnetopause shapes scaled from Earth. And this one that you see here is for a case where the ratio of the magnetic moment of Mars to that of Earth is 0.001, 1/1000th. And while we're at it, Van Allen dug up this paper from about Blackett's law. Actually, it was in 1907, maybe? Anyway, where this is the relationship between the magnetic moment of a planet. Beta is a constant of order 1, G is a gravitational constant. This is the angular momentum over c speed of light. And when you scale it, you find out, of course, that the angular momentum of Mars and Earth is 0.03. Therefore, you expect a magnetic moment of 0.03, if you believe this. And of course, we were finding that it's got to be 1,000 or a 1,000th or less. And but here's what we made of it. So that means that the surface magnetic field of Mars is less than 200 gamma, and hence they suggest that the solar wind will, on occasion and perhaps usually, have a direct interaction with the Martian atmosphere. Hey, how about that? This interaction may be of essential importance in determining the physical state of the atmosphere. I think we hear a lot about that these days. Also, it is evident that the atmosphere and surface are exposed to the full effects of solar and galactic radiation irrespective of latitude. This is from an all result. Okay. Now, this is today's view of Mars, courtesy of LASP and Dan Baker, his crowd. I'm not going to elaborate on that. We did, 2 years later, we essentially flew a copy mission. It was a copy spacecraft, Mariner 5 to Venus, And we determined again that there were no radiation belts. The magnetic moment ratio was in that range. The current view of the Venus-solar wind interaction is this. I'm not going to get into that. Mercury magnetosphere is truly unique, as you heard from the folks who were talking about MESSENGER. This is just a period of time that you see where we had a number of orbits, and you see all these electron spikes, which turned out to be ubiquitous. And if you saw one of Ralph McNutt's posters, you find out that some of these are only a few milliseconds wide, which is truly amazing. And also, MESSENGER found out that, in fact, the magnetic equator is displaced northward about 400 kilometers, that the plasma is hitting the southern hemisphere more than the northern hemisphere, and so on. So, and since time is moving, I better move on. These are the trajectories of Voyager 1 and 2, and of course the investigation of the outer planets started with Pioneer 10 and 11, and then continued with Voyager, and you see the trajectories. Jupiter's inner magnetosphere, many discoveries, the Eos plasma torus and aurora, and as you can see, sort of schematically depicted here, and many of you who have seen the detailed images from Hubble, you see the hot spots where this field-aligned current hits the ionosphere of Jupiter, and each one of the Jovian moons has a spot that you can follow by and large. Then we got an image of Jupiter's magnetosphere with the Cassini instrument during a flyby, and Barry Mock and Don Mitchell did a lot of this analysis, and you can see we also came up with a conceptual model of a cold and a hot magnetosphere and planetary nebula. In fact, so the sun, for scaling, is here, diameter of the sun. You can see how huge the magnetosphere of Jupiter is. Through some clever analysis and comparison with the Galileo proton data, Barry was able to interpret the existence of a neutral torus about Europa. And we now know, of course, that is so, and that Europa is an emitter of gas from the Hubble observations. So the big surprise was that Ganymede had its own magnetic field. And this is the magnetic topology that was, of course, it was seen by the magnetometer, but we inferred the magnetic topology from the energetic electrons. And you can see the pitch angle distributions. These are pitch angle distributions, pancakes, butterflies, the works, and you could infer what the topology of the magnetic field at Ganymede was. Going on to Saturn, this is our idea of what we were going to see with Cassini. We knew that there was a lot of dust and gas in the environment of Saturn, and we expected a lot of energetic neutral atoms. That's what actually happened. But going to the radiation belts, sure enough, there are Van Allen belts at Saturn, and you can count them. This is the count rate. We owe this nice schematic to Peter Coleman. And what happens is that, of course, you have the cosmic rays that generate neutrons that decay, and that's the source of electrons and ions that are then redistributed through diffusion, and they get lost when they interact, the ions in particular, with the moons. And we have mapped those pretty well. This is another schematic of these in both 3D and different view. But I want to show you this particular figure with data to point out that in 2005, Cassini discovered the new transient radiation belt between the orbits of Tethys and Dione. You can see it in Roussos et al. And that remained observable for several weeks, and it was the result of 3 intense solar energetic particle events. Does that remind you of anything of what we saw with Van Allen probes, temporary radiation belts? So it's apparently not an uncommon occurrence. The beauty of Cassini, of course, is it has the kind of instrumentation that we all dreamed about since the early days of the solar system, and I'm showing you this schematic from Mitchell et al. In 2009, which actually shows an energetic neutral atom image, and at the same time as an image of a UV image of the aurora at Saturn. And as this indicates, there is a connection between the two. And I'm going to show you a movie next, and I hope it works. I guess I should have asked for the sound to be connected, and I'll find out in the next go around. What you're seeing is a cloud of an emission. You can't hear the sound. I'm sorry about that. I should have asked the gentleman. Oh, you can. Okay. Auroral kilometric radiation, Garnet Curve special, as you all know about. And so what you see is the direct connection between the equivalent of a substorm, maybe, that moves in. You can see the brightening of the aurora, UV aurora at Saturn, and you can see the simultaneous emission of auroral kilometric radiation. And all of this is made possible now because we can have a global image, and we know where something happens, when it happens, and the extent of it. And that is depicted in the next schematic, which is kind of a 3D schematic that we put together that shows the magnetosphere of Saturn, and that you have a thick plasma sheet on the day side, you have a thin tilted northward night side plasma sheet. You also have the very strong convection that actually shoots plasma into the magnetosheath and out into the solar wind, especially oxygen, because oxygen has a large gyro radius, even on this scale, and it's easy for it to escape. So, and finally, a couple of other things about the new instrumentation. This is a composition plot of mass to charge, and you can pick out not only the mass of a particle, but its charge state. And this is with the same instrument, the flyby Earth, flyby Jupiter, and Saturn. And you can see the composition differences: nitrogen, N+, O+, here all the charge state of sulfur and oxygen. Here you see the water products, O2+, and so on. And it's a very powerful tool in really sorting out the sources of the radiation. I have to move on. The radiation belts at Uranus, all I can tell you is that there are Van Allen belts. There is, as we all know, the spin axis of Uranus is in the ecliptic, but the magnetic axis has a big angle to the spin axis. It kind of both in the flyby of Uranus and then on Neptune, again, a similar situation, even though the spin axes are tilted to the ecliptic, but not as much as Uranus, and yet the magnetic axis of the dipole are way off. And it played havoc with everybody's model of the dynamo, which they thought they understood. I was going to talk about some processes. This is actually Barry, I think, gave a talk about this in another session, so I'm going to skip it because I'm running late on time. And I haven't talked about processes. The magnetospheres are accessible laboratories for astrophysical processes in space plasmas. We like to say this, and it's really true. In fact, maybe, the next panel lecture ought to be about the processes and all the things that we have learned in magnetospheres about processes. But I want to move on to something else that is truly remarkable and one that probably most of us haven't thought about. This is the 37-year intensity plot for Voyager 1 and 2. The red is Voyager 2, the black is Voyager 1. This is a logarithmic scale here. You can see the number of solar cycles down here and the increase in galactic cosmic rays as we move away from Earth and into the outer heliosphere and local interstellar medium. And you can see the drop in intensities from when we launched in '77 down to about the year 2000, where we could hardly measure anything above background. And then a couple of years later, things began to really perk up, and eventually we crossed the termination shock. This is a mistake in the year. In 2004, at the end of 2004, there was a 3-order of magnitude increase in energetic particles. And then we were in the heliosheath for a number of years until 2012, when everything dropped out. And many people think we are now in the local interstellar medium. There are some descenders. One of them is a very good, is a fellow who introduced me. But notice, by the way, this doesn't show it, but Voyager 1 is in the northern ecliptic, and Voyager 2 is in the southern ecliptic, and the intensities are essentially identical. Why am I saying all this? Because when we crossed from the heliosheath into what some of us believe is the galactic medium, the crossing was very unusual. First, we saw some decreases in the intensity, and then the drop-off was dependent on what in the magnetosphere we all have learned to call pitch angle distributions, okay? And you can see this is the magnetic field measured on Voyager, and you can see that the intensity along in the magnetic field, this is going away from the sun, and this is coming towards the sun, really dropped fast. And the intensities perpendicular to the magnetic field took several weeks to go away. And you look at that, if you didn't know what was happening, and you would say, aha, this is a magnetic configuration. I'm in a trapped regime here. Well, of course, it's not quite clear unless you think quite so, unless you think in a big way about the solar dipole. But the fact of the matter is that you actually do have a belt of intense radiation beyond the termination shock, and it is both north and south. And we now know from energetic neutral atom imaging from both IBEX and Cassini, MIMI, this is a global image of the heliosphere, and we have this belt of energetic neutral ions, but of course energetic neutral atoms is what we image. Here's where V1 is, Voyager 1 and Voyager 2, and we have a belt and we have a tail, and there's intensity in the tail as well. So we now know that there is really a belt of radiation around the heliosphere, outside the termination shock. So, as time runs out, I'll just summarize. This is from a figure that Lanzarote and I published many years ago, and it simply shows the extent of the magnetospheres in planetary radii and how many moons there are in each one of these, and it's still so. So, the velanar belts in the solar system, first of all, we have 5 planets with intrinsic magnetic fields, Earth, Jupiter, Saturn, Uranus, and Neptune, and they have belts, very clearly. One planet, Mercury, that does have an intrinsic magnetic field, and all it has is transient electron bursts, but no durable belt. And of course, we have Ganymede that has an intrinsic magnetic field, but no belts as far as we can tell. I mean, we see the electrons, but they're mostly Jovian electrons that are there, and they go in and out. Venus and Mars, of course, don't have radiation belts. And Pluto, we think it's unlikely to have belts, but we must wait until July 15 of next year to make sure. I'm betting that it doesn't have belts. And by the way, July 15, 2015 is exactly 50 years after the encounter or flyby of Mariner 4 by Mars on July 15, 1965. So the new thing that I allege, and you can judge that, is the Voyagers have found a belt surrounding the heliosphere from about 90 to 122 astronomical units. It's indisputable that they surround the heliosphere. You might not say it's a classical Van Allen belt, but it is a belt that surrounds the heliosphere. And it's fitting, I think, that we should end with this picture here, which was on the 90th birthday of Van Allen, celebration in 2004, 10 years ago in Iowa City. This is a picture taken outside the Van Allen Hall, and it's remarkable in some ways because many of the pioneers of the space age are here. You see Gene Parker over here, Sue Nakasofu, Lou Lanzarote, see Norm Ness and Ed Smith. And see, for those of us who are older, I don't think I have ever seen them standing next to each other, let alone smiling. And of course, you have the front here, some of those of us who are older sitting there. And some have left, you know, like Frank McDonald and Van Allen and his wife, who went about a year after he passed on. George Ludwig is also not here anymore. It was the generation that essentially brought us the space science age, if you like. And they were all dedicated people that worked very hard and made it possible for all of us to have all this great fun all these years and work in a terrific field. So, with that, thank you all very, very much.